So this is a quick introduction to the permutations. There's lots of stuff for you on the web, but I also thought it might be useful looking through this and starting with this and then read the web stuff afterwards to help you get a better idea and better understanding of permutations. First of all, what do we mean by permutations? We mean the number of different ways that you can arrange a given number of objects in order. So the order or the arrangement matters. Another thing you'll find sometimes too is the purpose or the outcome matters. So for example, if I have 3 people and I want to select one of them as the president of a society, one as the secretary, and one as the treasurer, then we would have a number of different ways of arranging those 3 peoples with those office-bearing roles. But the order matters or the outcome matters. So once I've chosen one person for the president, if there's a rule that they can only hold one of those offices, then they can no longer be the secretary or the treasurer. So then I only have 2 choices to choose the secretary or the treasurer. And then when I've chosen that second person, there's only 1 choice left for the final one. Let's have a look at it with just symbols though. So here we have 3 objects, A, B, and C. And we want to think about how many different ways can you arrange them. If you've been doing your reading, you'll know how to do this quite quickly and easily. But if you haven't, here we go. So we could first of all take object A and follow it with B and C. Or we could follow it with C and B. This could be the same as, for example, or once I've chosen person A as the president of a society, then person B might be the secretary and C might be the treasurer, or person A being the president, then C might become the secretary and B might become the treasurer. But that's only 2 of the possible arrangements. What happens if you start with B and follow with A and C, or C and A? So if the order matters, if the arrangement matters, then each of these different arrangements is a permutation, and they have to be taken into account. You can easily check that those 6 arrangements are what we get using a simple tree diagram. So, for example, if you're picking 3 people in order or 3 objects in order from A, B, and C, for your first choice you can have A or B or C. The second choice, of course, once you go to your second choice, if you've already chosen A, then you can only choose B or C for the second choice. And similarly, A or C if you chose B first, and if you chose C first, you would only be able to choose A or B. By the time you get to your third choice, because you only have 3 objects to start off with, it's just a simple single choice for each of the remaining ones. If you have a look at it this way, by the way, the tree diagram is also a useful way of checking your calculations and your thinking. But notice for your when we have 3 objects, for your first choice you have 3 possibilities. And then you have, for your second choice, 2 possibilities. And for your third choice, 1 possibility. If we change it to 4 objects, for your first choice you've got 4, and then 3, and then 2, and then 1. This should look familiar. You've seen this in the form of what's called the fundamental counting principle, or sometimes called the fundamental counting rule. What happens if you've got any number? Let's say you were going to take n objects from 1, 2, 3 all the way through to n, where n might be 5, 6, 10, 100, 1 million, 20 million, and more. Well, for your first choice, you could choose n objects. So if there's 10 of them, you'd have 10 choices. For your second choice, you would now have 1 less. So if you've chosen 1 out of 10, you've now only got 9 left to choose from. And then, of course, you've got 8 to choose from if your original number was 10. But just using the symbols, you've got n minus 2, and so on until you get to the last one when there is only one choice. When you rewrite something out like this, in this form, we can say the number of ways of arranging an object, remember meaning arranging being the order matters, is n times n minus 1 times n minus 2 all the way down to times 1. To simplify this, we call this n factorial, and it's written with the symbol you can see there. So now we can say the number of ways of arranging n objects is n factorial. One of the key things to remember about mathematics is it's a form of shorthand. We're looking for quicker and simpler ways to write down something that we've worked out. If we've worked out a process for how things might be calculated, the number of ways of arranging or the number of permutations of an object, we're looking for a quick way to represent that in a shorthand form. So now we can say the number of permutations, that's different arrangements of n objects, is n factorial. In shorthand, we write it like this, with a subscript n being the total number of objects, p to represent permutations equals n factorial. However, sometimes you want to select just some objects from a bigger collection. Let's suppose we've now got 6 objects, or people, or things, A, B, C, D, E, F, and we want to choose only 3 of them. So as you can imagine, for our first one, you've got 6 options. You could pick any one of those. Let's take B. Now, for your second choice, you've got only 5 remaining, as you can see at the top of the screen. Let's take D. Now for your third choice, you've got only 4 options. Let's take E. So remember, our outcome was to find the number of ways of choosing 3 objects from a collection of 6. You can see the number there, 6 times 5 times 4, and that equals 120. If you wanted to check this, you could use a tree diagram if you've got a large enough piece of paper. Let's just look at a section of that. So your first choice, you could have had A or B or C, D, E or F. For any one of those, say for B, you then have 5 remaining objects you can choose, and for each one of those, you have just 4 remaining objects you could choose from. Just as you saw a moment ago, that's 6 times 5 times 4, giving us the total of 120. But can we come up with a formula for this? So as we do in maths, to help our shorthand, let's use some symbols. So let's label the number of objects in the collection as n. Mathematicians have a bit of a fetish for n, every time they're talking about a number of things. So in our first example here, n equals 6. Now let's label a number that we want to choose as r, which in this case was 3. Remember back to the fundamental counting principle. If we were arranging all 6 objects, we could just simply use the permutation rule for 6 objects, which would be 6 factorial. But in our case, we only chose 3 of those, 3 being r, out of a total of 6. And we found that the answer was 6 times 5 times 4. So if you're writing 6 factorial, you notice that the last 3 multiplications seem to be irrelevant. So is there a pattern we can find? Well, let's have a look if n equals 8 and r equals 3. So we're going to choose just 3 objects and find how many different permutations of those objects we can have if you're selecting them from 8 objects. Verify with the tree diagram if you've got a big enough piece of paper. But here's the answer. It's 8 times 7 times 6 equals 336. So if we wrote it, if we were arranging all 8 objects, you notice that, and we're only choosing 3, it's just those first 3 numbers of 8 factorial that seem to be relevant. The remaining numbers, 5 times 4 times 3 times 2 times 1, which is 5 factorial, is same as n minus r. What if n equals 8 and r equals 5? Once again, you can use a tree diagram or just a part of it if you're sensible, and the number of arrangements we can get is 8 times 5 times 6 times 4. So by now that sort of pattern should be looking familiar. So here we go. If we were arranging all 8, you would have 8 factorial, but because we're only choosing 5, notice it ends up being just those first 5 multiplications of the 8 factorial. And notice that 3 factorial is the same as n minus r, 8 minus 5. If n equals 13 and r equals 4, once again you could verify with part of a tree diagram, but the number of arrangements is 13 times 12 times 11 times 10, as you can see. Let's have a look at the formula for that. So once again, we haven't written it all out, but it's only those first 4 numbers of 13 factorial that seem to give us the answer. And the remaining bit, 9 factorial, is the same as 13 minus 4. So it looks like we can divide n factorial by n minus r factorial, or the factorial of n minus r, to get the number of possible arrangements. So in this example, 13 factorial divided by 9 factorial, it's all written out for you there. And just using your basic maths from school, you find that we can cross out all the same digits in the calculation, and you're left with just 13 times 12 times 11 times 10, which is what we found previously. So we can use the shorthand formula that you can see there to calculate the number of arrangements, the number of permutations when we select R objects from a selection or collection of N objects. There's an article called Article 1 posted for you, which gives a good review of the reasoning of the permutations and goes on to talk about combinations. So this would be a good thing for you to follow on with.